Good afternoon, class. So, till the earlier classes, we had discussed about the various topics related to the complex numbers, and we had seen how the complex number works. And prior to the complex number, we had seen various type of numbers such as natural numbers, counting numbers, rational numbers, or the fractions. Mainly, we had seen that earlier we had resolved all the queries using the natural number or the rational number. The rational numbers are the numbers which are in the form of p by q, where q is not equal to 0. If q will be equal to 0, then that particular number will be defined as will be transformed into infinity. So far, as far as complex numbers are concerned, in the earlier classes we had, and in the earlier classes of complex numbers, we had seen the various type of notations, how we are using different type of nomenclatures in order to describe the complex numbers. So suppose we had seen the first and foremost, the in the complex number we had seen the iota, that is under root minus 1, that is denotes as iota, which is represented as iota, which is the basic foundation of the complex number, that is the iota. It is under root minus 1, that is the iota. It is known as the complex number, the unit entity. It is known as the unity of the complex number, unity of the complex number. So in this case, we had seen various type of things such as how to transform a particular number into the complex number. In this class, in the today's class, we will be seeing how we are representing any number in the form of the complex number. First and foremost, we will see how we are writing a particular number, that is in the form of a plus ib. In the form, suppose we are writing a complex number in the form of a plus ib, and we are denoting it as a z, where z equates a plus ib, where z equates a plus ib in this case, and a will be equal to the real part of the complex number. The a denotes the real part of the complex number, real part, and ib, this particular part, this part, and this part, this I will be marking with the black ink. It is written in with the black, and ib, it is representing the complex number, complex part. It is ib. When any alphabet it is adjoined with the complex number I, then it becomes a complex entity. So ib denotes the complex number part. ib denotes the complex number part, complex number part. So any number it is written as, suppose z is a particular number, and if it is bifurcated into two parts, that is real part and the imaginary part, and if it is written in the form of z is equal to a plus ib, where a denotes the real part and ib denotes the imaginary part. So in today's class we will be seeing some type of concept which will render more transparency. First and foremost, we will see how we are writing a particular number. We will see some of the examples which will make our concepts more clear. So first and foremost, we will see some of the examples such as, suppose if any particular number is there, it is written in the form of 7 plus 2i. So it is written in the form of 7 plus 2i. So in this case, 7 will be the real number. The real part of this, it is 7, the real part. And 2i denotes the imaginary part. So this is the imaginary number. So it is the imaginary part. So as a whole, we will be saying that a particular complex number can be bifurcated into two parts, which is entitled as real part and the imaginary part. The real part are generally the natural numbers, which we can say it starts from 1 and it can go up to infinity. And as far as the imaginary part is concerned, it is associated with the alphabet I, which we had already studied. I is denoted as under root minus I, that is, and under root minus 1, that is iota. So basically we will be seeing some of the more examples, such as we had seen 7 plus 2i. Now if it is written in the form of z is equal to minus 1 plus I, in this case the minus 1 will be entitled as the real part, and I will be entitled as the imaginary part. So as an example, we had seen some of the cases which had rendered more transparency on our concept, and we had seen how a particular complex number can be bifurcated, can be expressed in the term of real part as well as imaginary part. So furthermore, we will be saying some of the more concepts associated with the complex number, and it will be easy for us to understand the concept, the latent concept which is hidden there. So we'll be seeing some more examples here. It will be easier for us to understand the part. Suppose we have to equate the complex number. The two complex numbers are there, and we have to check whether the both complex numbers are equal, and what are the means and what are the, you can say, the latent concepts are there, how they are equal. So we'll be seeing some of the examples. Suppose in this case we have to say equality of a complex number. Equality of a complex number. Equality of a complex number. So suppose if it is given in the question that the two complex numbers are equal, suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. The two complex numbers are said to be equal if the real part of first complex number is equal to real part of second complex number, and imaginary part of one complex number is equal to imaginary part of the other complex number. So z1 is the first complex number and z2 is the next complex number. As per the concept which I had stated, that the real part of the z1, the real part of the first imaginary number, that is a1, will be equal to a2. This part, this a1 will be equal to a2. The real part of one complex number is equal to real part of the second complex number, and the imaginary part is generally associated with the I. So in that case, the imaginary part, we have to leave I and we have to check b1. b1 is equal to b2. We have to exclude I and we have to take the alphabet which is associated with a complex number, and it will be like this. So the concept is the two complex numbers are said to be equal if the real part of one complex number is equal to real part of other complex number. So in that case, the both complex number will be equal. So we'll be seeing some of the examples which will render more transparency, and it will be easier for us to solve the particular problem. Suppose z1 is equal to 2 minus iy and z2 is equal to x plus 3i. It is given in the question that these two complex numbers are equal. So if those two complex numbers are equal, as per the prior statement which I had stated, that the real part of the complex number z1 is equal to real part of the complex number z2. So in that case, x will be equal to 2 and y is equal to minus 3. So we have to check here the I and minus I, so y is equal to minus 3. So we are saying that the two complex number are equal now, and if the two complex number are equal, the real part of first complex number is equal to real part of second complex number, and imaginary part of one complex number will be equal to imaginary part of second complex number. So in this way, both the complex numbers are equal. So that is the basic concept, and now we'll be seeing some of the properties of complex number. How there are certain properties based on which how complex number behaves, the characteristics of the complex number based on the different scenarios. We will be seeing some of the examples. So it is the equality of the complex number which we had seen. Now we will be switching over to the properties of the complex number. And after studying the properties of the complex number, it will be easier for us to understand the basic concepts which is hidden there. Suppose it is written there addition, the properties of the complex numbers. The various properties of the complex numbers. The various properties of complex numbers. The various properties of complex number is there. Addition of a complex number. First we will see the addition, the basic operations. The operations which we are executing when we are handling any natural number, the same it is having resemblance with the complex number also, but there are certain variations are there which we will be seeing how to take into account such type of variations. So first and foremost, it is the addition of a complex number. Suppose z1 is equal to a1 plus ib1 and z2 is equal to a2 plus ib2. If we have to add these two complex numbers, the first and foremost the condition is we have to add the real numbers together, the real number of both the complex number together and the imaginary part of both the complex number together. We have to check what is the real part of this complex number, and secondly we have to switch over to the complex part of the imaginary number. Suppose in this case the z1 is equal to a1 plus ib1, so sorry, it is ib1 and it is ib2. So in this case we will be saying the real part of z1 is a1, the real part of z1 is a1 and the real part of z2 is a2. So we have to add like this, we have to add the real components of the complex number in both the cases and the imaginary components in both the cases. So the imaginary part will be imaginary part of z1 is equal to b1 and imaginary part of z2 is equal to b2. So when we are adding, we will be seeing that it will be a1 plus a2 plus I b1 plus b2, and it is be a new natural number which will be entitled as z3. So the summation of z1 plus z2 will be a new product, that is z3, and z3 will be the summation of the real components as well as imaginary part components, and the final answer will be z3 is equal to a1 plus a2 plus I, it is common, b1 plus b2. We will be saying some of the examples here, so it will be easier for us to understand the concept. So we will be seeing some more examples. Suppose the question is like that, we have to add the two complex numbers. So z1 is equal to, it is 2 plus 3i, and z2 is equal to 3 minus 2i. So in this case, if we have to add both these complex numbers, first and foremost we will check what is the real component of the complex number in both the cases. Similarly, we will check what is the imaginary component of the both these complex numbers. So z1 plus z2, the real part will be, the real part of z1 is equal to 2, real part of z2 is equal to 3. So we will be seeing the imaginary part also. Imaginary part of z1 is equal to 3 plus 3 and imaginary part of z2 is equal to minus 2. We will be adding the similar operations which we were executing when we were handling the natural numbers. So in this case, the addition, post addition, we will be finding the real part will be, it is equal to 2 plus 3, 5, and the imaginary part will be 3 minus 2 plus 1. So a new complex number will be generated and it will be entitled as z is equal to 5. Z is equal to 5 plus I. So that is the answer, z is equal to 5 plus I. This is a new natural number which is the combination of both the natural numbers, and we had during the course of operations we had seen how to take the real part of the both the natural complex numbers and the imaginary part of both the complex numbers. So this is the basic additions when we are executing any complex numbers, and we will be seeing some of the properties of addition of the complex number, and it will be easier for us to solve the basic numerical problems. So we have seen the equality of the complex number and the addition of complex numbers. We had seen the equality as well as addition of complex numbers. As far as the equality of the complex numbers are concerned, so far we had covered two topics related to the complex number. The first one was equality of the complex number. In the equality of the complex number, we had checked how to trace the real part of the real components of the complex number in both the cases and the imaginary component, and we had to equate both. The real part will be equal to real part and the imaginary part will be equal to imaginary part, and post operation we will be seeing a new product, and we will see how both the complex numbers are equal in both the cases. Secondly, we had seen the addition, the basic addition of the complex number. In that case, we had seen how to trace the real component and the imaginary component, and how to add both the components, and the new product will be formed, that is Z3, which will be equal to the summation of the real component of the complex number as well as the summation of the imaginary component of the complex numbers. Now we will be seeing some of the properties of the addition of the complex number, which will render more transparency. So the properties of addition. Properties of addition of complex numbers. Addition of complex numbers. So this topic, it is the subtopic of addition of complex numbers. We will be seeing the properties, some of the properties. The first property is commutative. Commutative. So in this case, as far as the commutative property of addition is concerned, in this case, suppose Z1 is equal to A1 plus IB1, and Z2 is equal to A2 plus IB2. So in this case, we will be saying, as far as the commutative properties of addition is concerned, Z1 is equal to Z2. Okay, so no, it is Z1 plus Z2. Okay, Z1 plus Z2 is equal to Z2 plus Z1. It is the commutative property. Suppose A plus B is equal to B plus A. Similarly, in the same case also, Z1 plus Z2 is equal to Z2 plus Z1. So we will be saying, so in this case we will check how we will be verifying also. Suppose we add Z1 plus Z2. So Z1 plus Z2 is equal to A1 plus A2, A1 plus A2 plus I B1 plus B2. Now we will see Z2 plus Z1. Z2 plus Z1 is equal to, similarly, we will be taking the real component together. So A1 plus A2 plus I B1 plus B2. So in both the cases, we had seen that the result obtained post operations Z1 plus Z2 is equal to Z2 plus Z1. So it establishes the relationship, and it signifies the characteristic of the complex number under the addition topic, that it is commutative in nature. That is, Z1 plus Z2 is equal to Z2 plus Z1. That is commutative nature. Second is associative. Associative means that suppose A plus B plus C is there. So in that A, B and C, three components are there. In that case, if we are taking together A plus B and we are separating C, and we are adding together A plus B in a bracket plus C is equal to A plus C in a bracket plus B. So that property is known as the associative properties. It is a commutative property. The next step is associative. We will be seeing the example of the associative, which will render more transparency and make our concepts more clear. It is a commutative property. Secondly, we will be seeing the property is associative. The second property is associative. Associative. As far as the associative name is concerned, it is literal meaning of associative is making together. Suppose if there are three components are there, Z1, Z2 and Z3. Understood? And if we are taking Z1 plus Z2 together, and we are adding Z3 as a separate entity, and if we are, as per the associative property is concerned, if we are taking together Z1 plus Z3 and we are keeping out Z2 as a separate entity, then in that case also the answer will be same in both the cases, which will certify my statement that it is associative. The complex number, the addition of the complex numbers are associative in nature, and we will be saying some of the examples which will certify my statement. So we will be saying some of the examples. Suppose Z1 is equal to A1 plus IB1, Z2 is equal to A2 plus IB2, Z3 is equal to A3 plus IB3. So in that case, Z1 plus Z2 is equal to A1 plus I2 plus I B1 plus B2. That is the answer. And suppose we are adding Z3 again. So in that case, we will be saying we have to add the real components together. So final answer will be Z1. We are checking this Z1 plus Z2 plus Z3 is equal to A1 plus A2 plus A3 plus I B1 plus B2 plus B3. So that is the answer. Suppose now this is the complete answer of this statement. Now we are seeing that one, the right hand side, RHS one. The Z1 plus Z2, Z1 plus Z3 plus Z2. The similar answer we will be obtaining A1 plus A2 plus A3 plus I B1 plus B2 plus B3. So we had seen that in both the cases LHS equal to RHS, which is certifying my statement that addition of the complex number follows the trend of associative. We have seen both the properties here. The first one was commutative, the second one is associative. Now we will be switching over to the next property, that is existence of the additive entity. We will be seeing some of the examples which will certify my statement. First and foremost, we had seen so far we had covered about some of the topics. The first one was the notation of the complex number. The second one was the representation of the complex number in the two parts, the real part as well as the imaginary part. The third one which we had covered, it was pertaining the equality of the complex number. The fourth one was the basic addition of the complex number, under which we had studied the two topics. The first one was the commutative nature and the second one was the associative nature. Now we are switching over to the next topic of the complex number, which will certify my statement. That is basically it is the additive entity, existence of additive entity. We will be saying the existence of additive entity. Suppose if any complex number is there, Z, and if we are adding this complex number with the 0, understood, then in that case it will follow the first trend, that is commutative nature. That is, it will be equal to 0 plus Z. That is the existence of the additive entity. We will be seeing some of the examples which will render more transparency. Suppose if Z is equal to A plus IB, it is given there, and we are adding Z plus 0. So it will be like this only, A plus IB. In the right hand side, RHS, right hand side, similarly 0 plus A plus IB. It will be equal to Z, because we had taken Z which we had written as Z is equal to A plus IB. The similar result we had obtained here, A plus IB. So in this case LHS equal to RHS, which shows that there is an existence of additive entity also when we are taking addition into consideration. Now the under the addition topic, the last one is basically the existence of additive inverse. As the name suggests, as far as the name is concerned, additive inverse. Suppose Z is equal to A plus IB and minus Z is equal to minus A minus IB. If we are adding together Z plus minus Z, in that case the answer is 0. That is, there is an existence of additive inverse is there, which is certifying my statement. We will be saying the example which will render more transparency. Now it is given here, under the addition topic, there is an existence of additive inverse. There is an existence of additive inverse. So there is an existence of additive inverse. We had already seen the existence of additive entity. Now we are switching over to the existence of additive inverse. As the name suggests, The inverse, we had used the word inverse here. Suppose we are taking any complex number which is represented in the form of real as well as imaginary part, that is z is equal to a plus ib, and when we are adding the z part, that is when we are adding the z is equal to a plus ib with its, you can say, inverse, it means that we are subtracting it with the minus z. In that case, z minus z is equal to 0, plus z minus z will be equal to 0, which certifies that there is an existence of complex number which is inverse in nature. Suppose z is equal to a plus ib. Z is equal to a plus ib. Now, if we are adding a z plus minus z, so minus z will be equal to minus a minus ib. Now, if we are adding it a plus ib minus a minus ib, finally we are obtaining the number as 0. So we can say there is a particular complex number z whose additive inverse is minus z, and when we are adding both the entities together, we are obtaining the number as 0. That is z plus minus z is equal to 0. That is quod erat demonstrandum, QED, that is established. So, as far as the complex number topic is concerned, we had seen the various topics. The first and foremost, we had seen the complex number. These are the numbers which are imaginary in nature. The first, we had seen about the natural numbers, the fraction part, the rational numbers, irrational numbers. Then we had switched over to the complex number. Under the complex number, we had seen the importance of under root minus 1, that is iota, how it is playing a vital role in solving complex numerical problems. Now, post that, we had seen the various properties of the complex number. We had seen how we are representing a complex number into two components. That is, the first part is the real part and the second part is the complex part. That is, z is equal to a plus ib, where a denotes the real part and b denotes the imaginary part. Secondly, we had seen the equality of the two complex numbers. The two complex numbers are said to be equal if the real component of first complex number will be equal to the real component of the second complex number, and the imaginary part of the one complex number will be equal to the imaginary part of the second complex number. Thirdly, we had seen the various properties of addition, how we are adding. The basic properties of addition is when we are adding the two complex number, first and foremost, we are checking the real component of both the complex number. Then we are switching over to the complex part. We are just extracting out the real part and the complex part, and we are adding both the entities. And under the universal topic of addition, we have to go through the subtopic of the properties of addition, that is commutative nature, associative nature, additive inverse, and we had seen this additive inverse also and additive entity also. So far as the complex number topics are concerned, we have gone through the addition part, and in the next class mostly we will cover the subtraction part, subtraction, multiplication and division, and thereafter we will be switching over to the complex numerical problem, and then you can say on a daily basis and on an easier way we will be trying to solve all the complex number problems easily. So far, if any problem is there, and just ping a message on my WhatsApp or my YouTube account. I'll be saying all those messages and will try to resolve all the queries within the shortest stipulated time. Till then, thank you for the day.